All right, so we're going to try to get through this amine chapter this week. Essentially, the amine chapter, in my opinion, is the last of the synthesis-heavy chapters. All right, so last week we talked about preparation of amines. We said that we can do substitution reactions to make amines, but what's the problem with substitution? Does anybody remember? We tend to over-alkylate too, so we get a huge mixture of products. So this route works a little bit better where you use sodium azide, do SN2 substitution, and then change that azide group into an amine using either catalytic catalytic palladium and carbon with hydrogen or lithium aluminum hydride. The main pitfall to this is how toxic sodium azide is, and it's potentially explosive. Yep.
Clarification for clarification's sake, is that an LD50 of Na-N3, or is that a...
It's a good question. I think that's the LD50, so it'll kill 50% of a population. Yep.
Like, just spilling it on yourself, is that enough, or do you have to ingest?
That's a good question. So usually when you look up LD50 values, they have different modes of exposure, whether or not it was, an injection or oral or skin contact. I can't remember which one this is. Yeah. Either way, it's not a fun reagent to work with, and most chemists prefer to avoid it. Which leads us to the next reaction. All right, the next reaction is a lot better. This is called the Gabriel synthesis. And the Gabriel synthesis is preferred by a lot of chemists because it's far less hazardous, far less toxic, and it avoids the generation of gas. So if you're doing the reaction with sodium azide and creating nitrogen, and you're trying to make a metric ton of some pharmaceutical product, it's not a good idea to be making a lot of gas, right? So this avoids a lot of the pitfalls. So let's take a look at the overall reaction. All right, so the first starting material we work with looks like this. It's a bicyclic ring system. This should be a nitrogen. That's a poorly drawn nitrogen. This is called phthalimide. So that's the classic starting material for the Gabriel synthesis. And the overall reaction is kind of steppy. Yep. I just kind of omitted lone pairs on everything, but we can draw them in. All right, so the first step in this reaction is to treat it with the strong base. Usually sodium hydroxide is good enough. Where do you think the most acidic proton is? Off the nitrogen, so we'll deprotonate that. And then step 2 would be to do SN2 chemistry with some sort of alkyl halide. This is much more controllable than a normal alkylation with ordinary amines. Why is that? Think about the lone pair on the nitrogen. It's resonance delocalized, right? So the lone pair isn't as nucleophilic as a classic amine lone pair, so we can control SN2 substitution better. And then last but not least, we have a couple of options. One option is to treat this with acid. However, I'm going to make a note here that if you do this one, it's slow. Or if you want to get fancier, you can use hydrazine, which is really fast. All right. So the key thing that will occur here is you'll generate your new amine. That's the desired product, right? So this is what our target molecule is, and then our byproducts can vary depending on step 3. So if we use acid, what you'll end up making as a byproduct is a dicarboxylic acid. So that's one option. Or if you use hydrazine, you're going to get something a little bit different. You'll get this new bicyclic ring system in. So this is if H3O plus is used. This is if hydrazine is used. Oops. Does that make sense? So the byproducts will vary depending on which reagent you use for step 3. All right, the mechanism, like we said, is pretty straightforward though. In fact, we were able to kind of infer based on the reagents. Right. This one rattling. There we go. All right, so step 1 we know will be deprotonation. So we're going to just pluck off that proton coming off of nitrogen. We know that that's going to be the most acidic proton because the conjugate base is resonance stabilized, and we're just simply not going to deprotonate any of the aromatic protons. That's just not ever going to occur. So normally nitrogens really aren't that acidic, but in this case, that nitrogen is relatively acidic because the conjugate base is resonance stabilized. And then in the next step, we said we're going to treat this with some sort of alkyl halide. Again, we need to make sure that it's unhindered. Otherwise, it's just not going to do SN2 chemistry very readily. Now we've got our alkylated amine. And then if we think about this, this whole functional group is just an amide, right? We know that amides can be hydrolyzed into carboxylic acids by treating it with acid and heat. So that's one option. If we do that, we're not going to show the full mechanism, but like I said, you'll get that dicarboxylic acid to kick out. Along with your amine. And normally your amine that you generate will be protonated. Why is that? Yeah, because we're using acid, so sometimes you might even see a follow-up step with base to help neutralize that. Alternatively, like I said, you could use hydrazine. If we think about this, the main reason why this is much faster is because the lone pair on the nitrogen is way more nucleophilic than a lone pair on oxygen, because nitrogen's not as electronegative. So in either situation, you can get the reaction to occur. But we're not going to show the full transformation for this one. The one benefit to doing this one, though, is you don't really have to worry about getting your protonated amine because you're not running it under acidic conditions. Does that make sense? All right. So let's try a little bit of a warm-up problem, and I want you to use this Gabriel synthesis. Okay, so in this reaction, we're going to start with this starting material, and our goal is to make the following product. So I'll give you a minute to think about this, and you can check with your neighbor too. So let's try working through this a little bit together. What I want to do is plan out our Gabriel synthesis strategy. So we know with the Gabriel synthesis, we're always going to start out with that same starting material. It looks like this. And then step one was what? NaOH, we need a strong base. All right, step two, what would we need? We would need some sort of alkyl halide. And if we look at it, right, the alkyl halide must have had this. However, instead of a nitrogen there must have been some sort of leaving group, right? Okay, so let's plug that into step two, and then we'll figure that out later. So that would be our intermediate, or our reagent for step two. And then step three, let's use hydrazine. And that would give us our desired product. However, we need to figure out how to make this. Okay, so down here, we need to figure out how to make that. So let's kind of work backwards through this. What do you think the intermediate must have been before we got that bromine on there? Some sort of alkene, right? Okay, so if it was an alkene, we must have had our double bond right there. Does that make sense? What reagent would we need? So if we did HBr, we would get bromine installed on the tertiary carbon, but what's our workaround? Roar. We need HBr and peroxides, right? So if we do that, then we get that anti-Markovnikov halogenation. So that's going back to second term. All right. And if we think about this one, well, we must have had a leaving group somewhere in order to make that alkene. Makes a lot of sense that it wouldn't be in the same position. Otherwise, we'd just be running around in a circle. So what reagent would we need here? What's that? T-Bach? Potassium terbutoxide. Why wouldn't we want a small base? It would favor the more substituted alkene. All right, so we're almost there. How would we get this halogenation to occur using our starting material? Yeah, Br2 and UV light. So now we can kind of plan out how to make that intermediate even. So these are pretty powerful reactions. However, it is good to kind of go back and review a lot of the old chemistry that we've seen. All right, for bonus points. Well, not really bonus points, but what's the name of this? So remember, we want the longest carbon chain containing our important functional group. Yep, so Armand said that it would be 2,3-dimethyl. Oops. Our longest carbon chain is a butane, and we've got our amine off carbon 1. So it would be 2,3-dimethyl 1-butanamine. So make sure that you do go through and brush up on the naming. Don't be surprised if that's on the next exam. All right, does that make sense? All right, so this is a pretty popular reaction. In fact, it's still used somewhat regularly today. Does anybody know one of the kind of pitfalls of this reaction? Or a complaint even? Atom economy. The atom economy for this is terrible, right? We're producing a lot of waste here. So it's not ideal. If we can improve atom economy, that would be better. All right, so that leads us to our next reaction. We can prepare amines through a different method called reductive amination. So I'll show you the overall idea of this. What we're going to do is we're going to start out with a ketone or an aldehyde. Doesn't really matter which one you start with, you just need a ketone or an aldehyde. And then in our first step, what we're going to do is we're going to treat this with buffered conditions. So I'm going to put H plus in brackets, right, because we know it's buffered. It's just saying acidic buffered conditions, right? All right, and we've got ammonia, and we're going to remove water. What sort of product are we going to make? An amine? Not at this step.
Eventually we'll make a meeting.
So remember back to our aldehyde and ketone chapter, we've got a primary, or in this case, ammonia is a regular amine. Will it make an imine or an enamine, do you think? An imine. All right, and under acidic conditions, you can actually keep this as the charged species. This is called the aminium ion. Right, it's just a protonated imine. All right, and then in the next step, the whole idea behind this is we can reduce this. Right, so if we reduce that double bond, we're just going to go ahead and make an amine. So it's kind of a novel workaround to get an amine to be made, right? All right, let's take a look at some problems though. So hydride reduction is the first most logical step. What are the two hydride sources we use for reducing agents for the most part? Yep. So we use LAH often, or what's the other one? NaBH4, sodium borohydride, is problematic. Meaning we can't use them in this situation. Does anybody know what a potential problem might be? Yeah, and if we think about it, oftentimes in this step, it's under equilibrium conditions, right? So if it's under equilibrium conditions, what do you think LAH or sodium borohydride could do? It could reduce the ketone or the aldehyde before your imine really is formed in an appreciable amount. So that is a big problem with this. We can't use a normal hydride source. All right, so I'll kind of show you what I mean by that. Is chemists like to do this as a one-pot reaction. This is just a bad example to show you what's wrong with it. You can write it down if you want to show what not to do. So this will reduce your carbonyl bond really fast and won't give you your amine that you want. All right, so chemists had to figure out a hydride reducing agent that worked well to reduce an aminium ion without reducing aldehydes and ketones. They had to find something with a little less oomph to it. All right, so I'll show you kind of the scale that we're working on here. What's our strongest hydride source? LAH. And then we've got sodium borohydride. Then I'll put weakest or weaker. What could be a method for making this less willing to donate a hydride group? Think about it this way, right? Over here we've got I'm going to draw out the major components. Oops. All right, so what's something we could do to maybe mitigate the severity of that negative charge in the center? Anybody have any ideas to make this a little bit more stable, less reactive? What can we do to stabilize negative charges? We could do resonance. That's one option. What's another option? We could have something pulling that electron density away from that center too, right? So maybe some sort of strong electron withdrawing group. And that's exactly what they tried, was they tried making new hydride sources where instead of having a hydrogen in one of these positions, throw on some sort of electron withdrawing group in order to kind of tone down the reactivity of this molecule. And the one that they ultimately settled with is this. So let's draw this out. This is sodium cyanoborohydride. This electron withdrawing group really lowers the reactivity of this molecule. Due to induction. And resonance for that matter. We'll just do to electronegativity. We'll clean it up. All right, does that kind of make sense? All right, so it's a new hydride source. It's really, as far as we're concerned, only used to reduce aminium ions, though. All right, so let's take a look at this in action. The nice thing with this is you can do a one-pot reaction with your buffered conditions. You can react this with an amine and sodium cyanoborohydride. Yep. That's a good question. I think it does depend on the amine that you're working with, but I think normally it's about 4 or 5. Yeah. But in this example, it's nice because we won't run into reducing that carbonyl. We can make the aminium ion at equilibrium, and this will only reduce the aminium ion, and therefore pulling it out of equilibrium. Does that kind of make sense? So even though that aminium ion formation is in equilibrium, once you reduce the aminium ion, you're driving it to completion. So it's a pretty novel workaround. The other nice thing with this is it is super versatile. All right, so I'll show you what I mean by that. So we can make this amine. We can make that amine. Or we can make this amine. So the top amine, is it primary, secondary, tertiary? How would we define that? It's primary. So we can make a primary amine that way. We know it's primary because the nitrogen is only bonded to one carbon. What about the next one down? Secondary. And then last but not least, we can make tertiary. We couldn't do this easily with the Gabriel synthesis, right? So this allows us a lot more flexibility in the amines that we're making. All right, so in the first one, we already saw this as an example that we can use acid, ammonia, and sodium cyanoborohydride. This one's going to look pretty similar, but what will the amine be? Well, it's got to be a primary amine, right? In fact, I'm going to make this R prime just so we can differentiate that from our other R's. And then down here, kind of same idea. And in both of these bottom reactions, we'll still use sodium cyanoborohydride. Does that make sense? It's a pretty neat reaction. This is super common in the pharmaceutical industry, this particular type of chemistry, although the reducing conditions can vary a lot. Oftentimes in the pharmaceutical industry, they'll actually use a catalytic reducing system for obvious reasons, right? If you're a pharmaceutical company making metric tons of something, you don't want to go through stoichiometric amounts of reagent. All right, so I'll show you an example. Yeah. No, they can be different for the tertiary example. So you could have two different types of R groups. All right, so I'll show you my next example. I like showing pharmaceutical ones. Yep.
Does Stuart explain, like, if you have like two phenyl groups coming off, is that going to be like too bulky to have a reaction?
So sterics will play a role, but this is really versatile. It'll accomplish a huge number of bulky groups, I should say.
So it'll get there eventually, it's just if bulky, it'll slow down.
Yeah, it might slow it down if you're working with really bulky reagents. All right, so let's take a look at this one. This is kind of a bulky molecule. So we've got a carbonyl here, got a wedge down here. All right, so big molecule, right? All right, so now we need to figure out what our product will be at the end. Well, we know we only have one carbonyl. We've got a primary amine, so we're essentially going to swap off that oxygen for the nitrogen, and we're going to go from a double bond to a single bond. The stereocenter down here is going to stay put. And if you notice, we made a new stereocenter right here. So this could be either R or S, right? It's no longer sp2 hybridized. This is Zoloft. Zoloft is sold as a racemic mixture. All right, does anybody know what Zoloft's used for? Antidepressant, anti-anxiety drug. So one of the big blockbuster drugs that was developed in the early 90s. So pretty cool. All right, next one. Is anybody a fan of Breaking Bad? A few people? All right. You can't report me on this one because it's actually in your textbook. All right, so there's an episode, I'm going to give away spoilers, in Breaking Bad, where he goes and steals some reagents, right? And then he gets caught stealing reagents, and the DEA agent goes, oh, it's an old school biker crank cook, and they call it P2P cook. All right, does anybody know why it's called P2P? What is this starting molecule called? What's the most important functional group? Ketone. So longest carbon chain, be 1, 2, 3. We got this group coming off the side. What's that called? Phenyl. All right. So this would be phenyl to propanone. P2P. So Walter White in Breaking Bad steals a bunch of phenyl 2-propanone. All right. And his goal, as I'm sure most of you are aware, is to make methamphetamines. I know, right? That's why you got to pay science teachers more so they don't do this. All right. So if you're a fan of the show, right, the other reagent that he stole was methylamine. So methylamine makes sense here, right? Because essentially what he's trying to add on is this entire group. So he ends up stealing a bunch of methylamine throughout the show.
I mean, stealing is cheaper than buying it.
And so this is amphetamine. All right, the big disclaimer I always like to say is if you ever try to purchase phenyl 2-propanone or methylamine from any industrial supplier, you will immediately be on a list and have a DEA agent making some phone calls to you. So really, you cannot purchase either of these without having a narcotics permit. It's actually become a huge hassle for the research chemistry fields, because now in order to get basic reagents like iodine, just plain old I2, that's a controlled substance now. This is also why it's a big problem in rural areas, is anybody with sophomore level organic chemistry experience can figure out how to make a lot of this stuff. These drugs are really, really potent, super duper nasty. That was one kind of qualm I had with the show, was they tended to glorify Walter White as making all this money instead of focusing on all the lives of the users that were destroyed. But yeah, that's just me getting on my soapbox. Anyways, let's stop talking about meth. All right. So we need to propose a synthesis of this molecule. I'll give you a hint. You can do it 3 different ways. Well, let's think about it, right? We know we made a carbon-nitrogen bond. So maybe this was the bond that we made, right? All right, so let's break this apart. We know that, I do love rings. We know that this has to be the nitrogen, right? Which tells us what about this carbon on the left? It used to have a CO double bond on it, right? All right, so now we can work backwards. We can say, well, maybe it started out as this as our starting material, right? Alternatively, we could say, well, what about this one? Well, this one could work too. So something like that? Yeah, could work. I mean, we're just throwing out ideas, right? We're just spitballing. All right, we'll do the next one. Don't make fun of me. All right, so this would be our last option. You're entirely correct that these two are the same. All right, which one do you think looks best, though? Do you like the middle one or one of the top or bottom ones? I'd probably do the top or the bottom one. The middle one, just to get the ring size that big, you're going to have a hard time doing that, right? We know that 6-membered rings are the preferred ring size. All right, so now we've made a good plan. All right, so our plan is to have an aldehyde off of there, right? Because if we go back up and we count, we had 1, 2, 3. I should also include the hydrogens on this nitrogen. It's good form anytime you have a non-carbon atom to show the hydrogens. All right, and then in our next step, we need to perform the cyclization. However, the amine is actually a part of the system, so we don't need any external source of amine, but we just need acid. And now we can go ahead and form this bicyclic ring system with nitrogen in the middle. So in my opinion, this is really powerful chemistry for us to exploit and utilize for synthesis problems. All right, so that's where we're going to stop today. The pod that's due tomorrow is asking you how to make a compound with an amine. You have a few options on the table, but you might want to explore a handful and then compare them with some friends before you submit it. All right, I'll see some of you in lab.